Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today in lecture 25, we will develop derivative rules for all 6 of the inverse trig functions. And we'll be able to do this pretty quickly because in our last lecture, we developed the inverse rule that tells us that the derivative of f inverse, the inverse of a function f, is equal to 1 over f prime with f inverse of x plugged into it. Our plan for today is to use this to find new formulas for the following derivatives. We'll have a formula for the derivative of sine inverse of x, one for the derivative of tangent inverse of x, and secant inverse of x. And in fact, we'll have derivative formulas for all 6 of our inverse trig functions that flow easily from the inverse rule. But before doing this, it's important to remember our triangles. If we have a right triangle with angle theta and hypotenuse 1, remember that the length of the opposite side is sine of theta, and the length of the adjacent side is cosine of theta. And this picture gives us our geometric interpretations of sine inverse and cosine inverse. If we have this triangle with hypotenuse 1, and we label the opposite side as x, it has side length x, then sine of this angle is equal to x. So since this is the angle where if you took sine of it, you would get x, this angle is sine inverse of x. So this is our geometric picture of sine inverse of x. Given a triangle with these side lengths as indicated, this angle is sine inverse of x radians. Likewise, if we have the same right triangle with hypotenuse 1, but the adjacent side is x, then cosine of this angle would be equal to x. So this angle is cosine inverse of x. It's the angle where if you took cosine of it, you'd get x. So this is our picture, our geometric description of cosine inverse of x. Likewise, if you have a right triangle whose adjacent side is labeled 1, then think about the opposite side. Opposite over adjacent would be opposite over 1, which is just opposite, and opposite over adjacent is tangent. So this opposite side is tangent of theta. Likewise, as we saw earlier, back in part 1 of the course, the hypotenuse of this triangle is secant of theta. So from this triangle comes our geometric pictures of tangent inverse of x and sine inverse of x. Given a triangle whose adjacent side is 1 and whose opposite side is x, if you took tangent of this angle, it would give you x. So this angle is tangent inverse of x. Similarly, if the triangle is such that the adjacent side is 1 and the hypotenuse is x units long, then secant of this angle equals x from our picture over here. So this angle is secant inverse of x. So we have 4 pictures here that tell us the geometric meaning of the inverses of sine, cosine, tangent, and secant. And we'll need all of these today. We are ready to get started. Just for reference, I've written down the inverse rule, d dx of f inverse of x equals 1 over f prime of f inverse of x. So on this slide, we will quickly come up with the derivative of sine inverse of x, the derivative of tangent inverse of x, and the derivative of secant inverse of x. Let's start with the derivative of sine inverse of x. We could use our inverse rule where f is the function sine here. So if f were sine, the derivative of sine inverse of x would be 1 over f prime of f inverse of x. Now f prime would be the derivative of sine, and that's cosine, and you're taking f inverse of x. Cosine of f inverse of x which would be cosine of sine inverse of x. So using our inverse rule, we get the derivative of sine inverse of x is 1 over cosine, which is the derivative of sine inverse of x. We'll simplify this a little bit. It actually has a really neat expression. Here we are taking cosine of the angle sine inverse of x. And let's look at our geometric picture of sine inverse of x from the previous slide. You take this right triangle with opposite side x and hypotenuse 1. The angle is sine inverse of x. And in this denominator, we are taking cosine of sine inverse of x. Look at this triangle. The hypotenuse is 1. Cosine of this angle would be the length of the adjacent side. Cosine of sine inverse of x, which is here, is the length of this adjacent side. And we could get the length of that adjacent side from the Pythagorean theorem in terms of 1 and x. The adjacent side squared plus x squared equals 1 squared. And solving that tells us that the adjacent side is the square root of 1 minus x squared, again by the Pythagorean theorem. So that's cosine of sine inverse of x. That's the denominator here. So making that substitution gives us 1 over the square root of 1 minus x squared. And that's our formula. The derivative of sine inverse of x is 1 over the square root of 1 minus x squared. We'll put that in the box. It's an interesting formula because in taking the derivative of sine inverse, you might expect to have a trig function in the answer somewhere. And initially we did, but it's interesting that it boils out to be a completely algebraic expression. Let's now move on to our next formula, the derivative of tangent inverse of x. We'll work that out here. We'll use our inverse rule. The derivative of tangent inverse of x would be 1 over the derivative of tangent with tangent inverse of x plugged into it. Just replace the f with tangent. Now the f prime would be the derivative of tangent, and the derivative of tangent is secant squared, as we know. So we get 1 over secant squared of tangent inverse of x. And again, this is 1 over f prime of f inverse of x, where f is tangent. And let's see if we can simplify this in the same way that we simplified the expression for sine inverse. Well, first of all, the secant squared of tangent inverse of x is secant of tangent inverse of x, whole thing squared. And look at what's being squared on the denominator. It's secant of tangent inverse of x. To make sense of that, think of our geometric picture of tangent inverse of x from the previous slide. Given a right triangle whose opposite side is x units long and whose adjacent side is 1, this angle, if you took tangent of it, you'd get x, so it's tangent inverse of x. So this is our geometric picture of what tangent inverse of x is. And here we are taking secant of that angle, secant of this angle. Well, remember, secant of this angle would be the length of the hypotenuse, and we can find the length of the hypotenuse by the Pythagorean theorem. It's 1 square root of 1 squared plus x squared. So the secant of tangent inverse of x that's being squared on the denominator, it's equal to the square root of 1 plus x squared. So this becomes 1 over the square root of 1 plus x squared, which is 1 over 1 plus x squared. So there we go. The derivative of tangent inverse of x is 1 over 1 plus x squared. We'll put that in the box. And this is our newest derivative rule. Let's move on to secant inverse of x. We'll work that out. For the derivative of secant inverse of x, we'll use our inverse rule, where f is secant. The derivative of secant inverse of x would be 1 over the derivative of secant with secant inverse of x plugged into it. Now the derivative of secant, remember, is secant times tangent. So we're getting 1 over, our f prime would be secant times tangent, but into it we're plugging in our inverse function, our secant inverse, and there are two places to plug that in, here and here. So the derivative of secant inverse of x is the reciprocal of secant inverse of x times tangent of secant inverse of x. And let's see if we can make sense out of this. We have a 1 in the numerator, and the secant of secant inverse of x, this first factor, what would that be? Secant of secant inverse is just of x, is just x. The secants cancel each other out here. Secant of secant inverse of x is x. And then right next to that, we're multiplying times tangent of secant inverse of x. Let's think about geometrically what's going on here. Tangent of secant inverse of x. Think of our picture of secant inverse of x. If we have this right triangle whose hypotenuse is 1, or whose adjacent side is 1, and whose hypotenuse is x, this angle is secant inverse of x. It's the angle where if you took secant of it, you'd get x. And here, we are taking tangent of secant inverse of x. In other words, tangent of this angle, and that would be the opposite side here. Well, what is this opposite side? We can actually find out from the Pythagorean theorem. 1 squared plus the opposite side squared equals x squared. So solving for the opposite side, it's the square root of x squared minus 1. So this picture tells us that tangent of secant inverse of x is the square root of x squared minus 1. That's this expression that's multiplied times the x. So we get the derivative of secant inverse of x is 1 over x square root of x squared minus 1. But we have to be really careful here. We actually don't have our formula yet, because remember that way back in part 1 of the course when we were talking about secant inverse, this triangle is only for x positive. So in making this calculation here and getting this expression, we've actually been tacitly assuming that x is positive. Remember that when x is negative, secant inverse of x has a different picture. Secant inverse of x is actually an angle that's bigger than pi over 2. It's bigger than 90 degrees. It's an obtuse angle. It looks like this. So when x is negative, things are interpreted this way. Secant inverse of x is this angle. And if you took tangent of that, as we're doing here, you're in the second quadrant, and tangent is negative. In fact, it's the negative of this length here. It's negative square root of x squared minus 1. So when x is negative, This square root of x squared minus 1 right here should be negative the square root of x squared minus 1. But also, in that case, x itself is negative, so you have a negative times a negative, which turns positive. So we can correct this by simply taking the absolute value of x, keeping it positive, and just using the positive branch of this square root of x squared minus 1. So that's our formula for secant inverse of x. We finally got it. The derivative of secant inverse of x is 1 over the absolute value of x times the square root of x squared minus 1. We'll put that in the box. So here we have quickly obtained 3 derivative formulas for sine inverse, for tangent inverse, and secant inverse. If you ever forget them, assuming you know the inverse rule, you can derive them again pretty quickly. But the best thing to do is commit these to memory, internalize them, and so you'll have them at your fingertips when you need them. So here we are, 3 new derivative rules, and we're halfway to our goal. We still need derivatives of cosine inverse, cotangent inverse, and cosecant inverse. And you can actually get these 3 rules using triangles and the inverse rule, as we did on the previous slide. And if you're so inclined, you should do that. But in lecture, we're going to get these 3 new rules in a slightly different way. Let's start with cosine inverse of x. I want you to remember something that we talked about way back in part 1 of this course. We worked out the identity cosine inverse of x equals negative sine inverse of x plus pi over 2. This holds for any x, at least any x in the domain of cosine inverse. This tells us that we can always get cosine inverse in terms of sine inverse. But also, if we're looking for the derivative of cosine inverse of x, that would be the derivative of minus sine inverse of x, which is negative this expression, plus the derivative of pi over 2, which would be plus 0. So right off the bat, we get the derivative of cosine inverse of x is negative 1 over the square root of 1 minus x squared. And that's a new rule. The derivative of cosine inverse of x is just negative the derivative of sine inverse of x. Let's play the same game for cotangent. Cotangent inverse of x, if you'll recall, equals negative tangent inverse of x plus pi over 2. You may want to go back and review your notes or read the text or go back to that lecture. But it's a fact. Cotangent inverse of x is expressible in terms of tangent inverse of x in this way. So if we want the derivative of cotangent inverse of x, it's negative the derivative of tangent of x plus the derivative of pi over 2. And that's just negative the derivative of tangent inverse of x. It's negative 1 over 1 plus x squared. And we have our next rule. Finally, for cosecant inverse, remember that it is equal to negative secant inverse of x plus pi over 2. So if you take the derivative of cosecant inverse of x, you just get negative the derivative of secant inverse of x, which is negative this fraction. So the derivative of cosecant inverse of x is negative 1 over absolute value of x times the square root of x squared minus 1. And there we have it. If you have remembered the first 3 rules, the rules for the other inverse trig functions come easily. They're all of the co-functions: cosine inverse, cotangent inverse, cosecant inverse. Their derivatives are just negatives of what the corresponding other 3 derivatives are. So commit these rules to memory, get some practice with them, and also think about them. And as you work with them and think about them, you'll realize that they really do make sense and they conform to your expectations of what derivatives do and what they mean. Take, for instance, the derivative of tangent inverse of x, 1 over 1 plus x squared. I'd like to graph f of x equals tangent inverse of x and also its derivative, and we're going to compare them. Here's the graph of tangent inverse of x, and you'll remember it has horizontal asymptotes at y equals pi over 2 and negative pi over 2. It looks like what's shown here. And let's also graph its derivative, 1 over 1 plus x squared. And I'll do that in blue. F prime of x equals 1 over 1 plus x squared. It looks like this. Now, notice that if you take f prime of 0, that's 1 over 1 plus 0 squared, or just 1. So f prime of 0 is 1. And also, as x gets bigger and bigger and bigger, this denominator, 1 plus x squared, gets even bigger. So its reciprocal is getting small, getting closer and closer to 0. So you're picking up a horizontal asymptote of the x-axis for our derivative f prime. So it has the basic shape as indicated here. Compare that to the graph of tangent inverse. Look at x equals 0. We have a positive slope there, and in fact, the fact that f prime of 0 equals 1 tells us this slope is exactly 1 right here at x equals 0, which certainly looks believable. Also, as x increases, think about these tangent lines. They're positive. Rise over run always looks positive. But as x increases, the corresponding tangent line is getting closer and closer to being horizontal. So although it's positive, it's getting closer and closer to 0, and that's exactly what the derivative is doing. Same for negative values of x. The slope is always positive wherever you are on tangent inverse of x. But if x is really big in the negative direction, these positive sloped tangents are almost horizontal, so their slope is almost 0, and you can see the derivative is almost 0 as well. So if you explore this kind of thing with the other rules that we have on this page, you'll find that everything really does match up to your expectations. I think it's worth doing. So here we go. Here's a list of our 6 new rules. And for each one of these, there is a corresponding chain rule generalization. For example, for the derivative of sine inverse of x, you could put in a g of x for the x and use the chain rule to find the derivative. You'd get the derivative of sine inverse of x of g of x as 1 over, this would be this with g of x plugged in for x. That's 1 over square root of 1 minus g of x squared. And that whole thing times the g prime of x. That's just the chain rule applied to this rule. So we get a corresponding generalized rule for sine inverse of g of x. And it's worth remembering and internalizing these generalized rules because we're going to have so many problems that are the derivatives of an inverse trig function of some other function. So you can quickly get the derivative of sine inverse of g of x with this generalized rule. Likewise, for the same reason, the derivative of tangent inverse of g of x would be g of x plugged in here. So you get 1 over 1 plus g of x squared, and then times the derivative of g of x. The derivative of secant inverse of g of x by the chain rule is 1 over absolute value of g of x times the square root of g of x squared minus 1 times g prime of x. is just plugging in a g of x here and here and multiplying by g prime of x. Similarly, we get the derivative of cosine inverse of g of x is what's stated here. The derivative of cotangent inverse of g of x is what's stated here. Note the negatives of these expressions. And finally, we get a generalized derivative rule for the derivative of cosecant inverse of g of x. This looks like a lot to remember, but really, as you're practicing this material, working exercises, all of this becomes very natural. It looks forbidding at first, but you'll get good at it very quickly, much quicker than you'd expect to. I've drawn a line here because you will see as you progress in calculus, especially when you get to calculus 2, it's really these top formulas that play the biggest role, and these bottom three below the horizontal line, they come up from time to time, but they play less of a role. And we saw an indication of that earlier when, for example, cosine inverse of x was expressible in terms of sine inverse of x. That's the essential reason. But still, for this course, do remember all of these and work with them. We'll start off with an example. Think about the derivative of sine inverse of x cubed minus x squared. That's the derivative of sine inverse of a g of x, where the g of x is x cubed minus x squared. So the answer is going to be this. It's going to be 1 over the square root of 1 minus that g of x squared times the derivative of the g of x. So 1 over the square root of 1 minus the x cubed minus x squared, whole thing squared, times the derivative of x cubed minus x squared. That's times 3x squared minus 2x. Simplifying a little bit, here's what we get for an answer. So pretty much in one step, with the cleanup half step, we've got our answer. It goes without saying that you could also get this just by applying the straight chain rule in either one of its versions without remembering this generalized chain rule, or this generalized derivative rule, and you'd get the same answer. Continuing with our examples, let's take the derivative of e to the power of tangent inverse of x. Now, this is the derivative of e to a g of x, so the answer is going to be e to the g of x times g prime of x. That's e to the power of tangent inverse of x times the derivative of tangent inverse of x. And here we're using our generalized exponential rule. But today we came up with the rule for the derivative of tangent inverse of x. It's 1 over 1 plus x squared. So here's our derivative. It's e to the tangent inverse of x divided by 1 plus x squared. Another example. Let's take cosine inverse of the function ln of x cubed minus x. Now remember, the derivative of cosine inverse was negative 1 over the square root of 1 minus x squared. So using the generalized rule here, we get negative 1 over the square root of 1 minus our g of x squared, where g of x is what's inside the cosine inverse, then times the derivative of that g of x. So we're almost done here. We just have to take the derivative of ln of x cubed minus x. And from our previous lecture, that's 3x squared minus 1 divided by x cubed minus x. The derivative of x cubed minus x divided by x cubed minus x. And of course, we bring this part down. So that's our answer. Maybe just a little cleanup here. Multiply this negative through the numerator, and you get 1 minus 3x squared and you get this denominator. We'll put the x cubed minus x out in front here. And that's our derivative. Next, the derivative of secant inverse of negative pi x. That's our next example. So this is the derivative of secant inverse of a g of x. So the derivative of secant inverse x, remember, is 1 over absolute value of x times the square root of x squared minus 1. But here it's not the derivative of secant inverse of x, it's the derivative of secant of minus pi x. So minus pi times x, that's a little g of x. So you're going to plug that g of x in here, and then multiply by the derivative of g of x. The derivative of negative pi x is negative pi. And here's our answer. A little bit of cleanup we could do here. The absolute value of negative pi x is pi times the absolute value of x. Bring this negative pi up into the numerator. And now you get some cancellation. The pi's cancel. And we get a derivative of negative 1 over the absolute value of x, square root of pi x squared minus 1. One more example. The derivative of 5x squared times tangent inverse of e to the x. So always when you're working out a derivative, you think about what's the first rule I'm going to apply. If you look at what we're taking the derivative of, it's a product. It's 5x squared times tangent inverse of e to the x. So the correct rule to start off with is going to be the product rule, which says take the derivative of the first function. The derivative of 5x squared is 10x times the second function, so that's times tangent inverse of e to the x. Then plus, the other way around, your first function, 5x squared, times the derivative of tangent inverse of e to the x. That's tangent inverse of a g of x, and that derivative would be 1 over 1 plus g of x squared times g prime of x, or 1 over 1 plus e to the x squared times e to the x. And just cleaning that up a little bit, we get 10x tangent inverse of e to the x plus 5x squared e to the x over 1 plus e to the 2x. That's our answer. So we've done 5 examples here, and of course you should work some practice exercises to get fluent at this. But we're done for today. The conclusion is we have 6 new derivative rules and their corresponding generalized rules that you get from applying the chain rule to the 6. That's it. And not only is that it for today, but these are the last of our derivative rules. That's it. No more rules. Well, maybe in part 5 of the course we'll have one more derivative rule that's sort of the grandmother of all of these rules. But for now, this is it. You can probably differentiate just about any function that you come across at this point, especially after working lots of exercises. So we have our rules. Coming up next, in lecture 26, it's not about rules, it's about meanings of the derivatives. We wouldn't be studying these things if they didn't have meanings. We now know how to find them. Next time, what they mean. I'll see you then. Goodbye.